Yes, everyone got it? T2?
94.96.
90 is coming.
Maybe
Which equation do you use, Doctor?
Sorry?
Which equation?
Which equation? Okay, I'm reading the equation. You check it. Like mCp delta T, it is for kerosene. M dot Cp delta T for kerosene is equals to M dot Cp for water. M dot Cp delta T for water.
Oh, okay.
Okay. So when you are writing the kerosene, then it is T2 minus T1. And when you are writing for water, it is T1 minus T2 because T1 is greater than T2 for water.
Okay. Or we can take absolute value.
For the difference, yeah.
Okay.
So you got it?
I will no, because I was searching.
Doctor, the kerosene is the cold fluid, right?
Kerosene is cold fluid, yes.
Doctor, when we design, we need to design for both parallel and counterflow.
Yes, doctor, we got it. 19.4644.
90.4. Okay. Yeah, Sultan, what are you saying? We design it for counterflow and parallel flow, right? So it is up to you how do for what configuration you want to design. You want to design it for parallel flow or counterflow. So usually the counterflow is more effective than parallel flow.
Okay.
Okay. So until now we have not taken that aspect in our design problem, right? Now we will take.
Yes.
So now you have all the temperatures, all the 4 temperatures, right? So
yes.
now you have to choose whether you are designing it for laminar flow or counterflow. So I have designed it for counterflow. So I have to calculate the overall, I have to calculate the log mean temperature difference for counterflow arrangement.
Yes.
So calculate the log mean temperature difference for counterflow arrangement.
I found it to be 63.
63, yeah, as in my case, yeah. I also got the same answer. Yeah. So the formula you need to know, and in my slide it is given the formula, and in the textbook also is given that log mean temperature difference for parallel flow and counterflow. It is given on page 407 also. Page 407. Page 407. Equation 8.9. It's for counterflow. So you can take from there log mean temperature difference 8.10 delta T for counterflow. Okay.
Yes.
Yes, Hadi, you were disconnected.
If kerosene is organic liquid?
Yes, organic kerosene. Okay, so you got it delta LMTD now, right? So, so I mentioned in my lectures that you can calculate the heat transfer, rate of heat transfer, and you have 3 ways of calculating it, 3 formula. The one formula, the Q equals to mCpT for cold fluid. Another formula is mCpT for warm fluid. And what is the third formula for calculating the rate of heat transfer?
Using the
heat exchanger equation. Yeah. So the Q equals to U A LMTD. Temperature difference. Right? So the U is your overall heat transfer coefficient. A is your area subjected
Area.
to heat transfer, and multiplied by LMTD. So you have Q, you have U, and you have LMTD. Then find out the area subjected to heat transfer. A naught. Now find out A naught. A naught.
Do you use it in Celsius or in Kelvin?
It will not make any difference. The Celsius, we are using throughout Celsius. It will not make difference, but we are using the
Temperature.
no, sorry, LMTD, right? LMTD, when you calculating the LMTD,
No,
right?
when we want to substitute it in the for the heat transfer function.
Degree
Okay.
Celsius.
Zero 0.47.
0.47. Good. Okay, now we have the area subjected to heat transfer. So from this area, can we calculate the length of the heat exchanger? Area subjected to heat transfer, what is this area equals to? If you have a heat exchanger, in terms of the heat exchanger dimension, what is this area equals to?
It's, the area of the
Area of the pipes.
outside.
Area of the
diameter
pipe. So what is the area of the pipe?
We have the diameter and we can find the length.
Yeah. So what is
the
the area?
outside diameter of the pipe. Outside diameter of the pipe multiplied by multiply
Multiply
by
by the length.
Okay. Yes. Pi dl. So pi multiplied by ODP, outer diameter of the pipe, multiplied by the length.
Yes.
But why outer diameter of the pipe? Why not the inner diameter of the annulus?
Because you know the heat transfer coefficient, when we calculate the heat transfer coefficient, we translated it into the outer side. So
Outer side?
yeah,
How did we do that?
we use the expression that was given on page number. What was the page number?
417.
417. No, 417 was 418.
418.
H. 418
Yes.
H. First we calculated
HI,
HI, and then we translated it to outer diameter.
HP.
So now we are calculating the heat transfer area. So that will be the outer area.
Oh, so this is so we calculated HI, then we converted to HP.
HP, right.
And this is like it's on the outer surface of the tube.
Exactly. So
Okay.
then we so now we can calculate the length. So how much is length now?
3.62 meter.
3.6. 3.6
Yes.
is the length. Good. So this is the length. So here, like if our selection, so what do you think? What is left to be calculated? Our heat exchanger dimensions are all clear. What is the inner pipe diameter? What is the outer diameter and what is the length? Everything is clear now, right? And we need to know that whether we are meeting our desired temperature or not. So we are meeting from 24 to 35, right? And from 95, it came to 90 degrees Celsius. Okay. So as for the heat exchanger design, we know this is complete. First step, this is complete. Another thing that we need to check that at what temperature you took the properties of water. If you took the properties of water at 90 degrees Celsius something, then you don't need to repeat it. But if you took like 60 degrees Celsius or something, 80 degrees Celsius, then probably you need to repeat it, because if it is 10-15 degrees Celsius temperature difference, then the properties will be changed. Then the length will come out to be different. You got my point?
Yes.
Okay. So now the length come out to be 3.6. So the 3.6 is not a very big length for double pipe heat exchanger. So this is acceptable. So this solution is acceptable. Other thing we need to check it, that how much is the pressure drop in the heat exchanger. So for that purpose, we need to calculate the pressure
Reynolds
drop.
number.
So the pressure drop, we need, if we go back, then you need to calculate the friction factor. For the friction factor, you need to calculate the Reynolds number. So for the pipe side, the Reynolds numbers, the same Reynolds number will work that we calculated the before. But for the annulus side, we need to calculate the Reynolds number again for the annulus side. And this time we will use the hydraulic diameter. So the Reynolds number is equals to rho v dh over mu. So it should be multiplied by rho, that is the density of water, multiplied by the velocity in the annulus side. So the annulus side is 1.8, and the multiplied by dh, hydraulic diameter, divided by mu, this one. So the hydraulic diameter is coming out to be Reynolds number coming out to be 1.21 10 power 5. Are you calculating with me?
Yes.
Okay, so this is the Reynolds number for annulus. Now we need to calculate the epsilon over d for both sides, for both cases, right? Epsilon over d, eps over d. So IDP, eps over IDP, and then eps over DH, hydraulic diameter, right?
Yes.
Hydraulic diameter. All right. So how much is this? The eps, that is the epsilon for copper, is 1.52 10 power 6, very small. So this coming out to be epsilon divided by the IDP. So the IDP is this value. And then here, this is going to be eps divided by the hydraulic diameter, which is this. So these are the values. And now we can see the chart, and if you have the formula, if you have the equation, you can type the equation in Excel, and then you can calculate the friction factor. So can you tell me what is the friction factor you can see from the chart corresponding to this Reynolds number and corresponding to this epsilon? So the F for pipe side and F for annulus side. Can you tell me?
Yeah, just a moment.
Yes. Yes, please.
We are now repeating the calculations using different properties.
No, we are not repeating. We are calculating pressure drop.
Oh, okay.
For the pressure drop, we are calculating the Reynolds number for the annulus side. Pipe side Reynolds number will remain same. We are calculating the Reynolds number for the annulus side, and we are calculating epsilon over d, and then we can go to the chart, or you can use any equation to find out the friction factor.
Okay. So this REA is different than the REA up there.
Yes, REA,
Okay.
this and that one is different because this is based on the hydraulic diameter.
Okay.
This is based on hydraulic diameter, and this was based on
Equivalent.
equivalent diameter.
Doctor, for the pipe, 0.016.
0.016, and for annulus,
1 minute. Zero point zero
0.18. Okay. Okay, and then we need to calculate the pressure drop. So for the pressure drop, when we are calculating, then what is the equation for the pressure drop?
F L over D.
Over D times V square over
So
2G.
the equations are
No,
given.
over
Yeah, equations are given on page 421. Page 421. So for the pipe side, it's the same as you calculating in your chapter 3, 4, 5. for the pipe side. It is exactly same, right? And for the annulus side, there are two losses. One is the friction losses and one is the minor losses. Minor loss is related to the ends of the heat exchanger, because at the end the fluid is turning and there is an inlet and there is a outlet because of the turning effect. Inlet outlet we are not considering, but there is a turning, because if you see the structure of the double pipe heat exchanger, then you will see that there is always a turn in the flow in the heat exchanger, right?
But
Like
Yes.
Right.
like in this case, can you see that? I'm sharing on the screen. Can you see that?
Yes.
Yes, yes.
How the fluid is turning. So due to this turning, there is a loss coefficient which is 1. So when you're calculating the pressure drop for the annulus side, then it is a friction pressure drop plus the minor loss pressure drop, which is 1. So the equations are given on page 421. So using those equations, we need to find out the pressure drop. So what is the pressure drop dP for the pipe side?
there is no something like this for the pipe.
What do you mean? Yeah, for the pipe, no. Yeah, because the pipe is connected straight away.
But okay, doesn't exit somewhere or something.
No, because it's just a joint. It's just a straight pipe coming in and going in and coming out. So it's just a joint, like a coupling.
Okay, I see.
Doctor, what's the density of the kerosene?
It's
730.
730.
It will be 3.6 kilopascal.
For the pipe side,
Yes.
3.6 kilopascal.
Yeah.
So, okay, 3.6 kilopascal. So I'm writing just in standard unit, everything. And for annulus,
Uh, 6.193 kilopascal.
6.193 kilopascal. Okay. So what is the constraint for the pressure drop? How much pressure you can basically bear in for the heat exchanger? How much you can bear? So the constraint is given in your book is the 70 kilopascal pressure for the pressure drop. So the actual constraint comes from the industry, depending upon the what are the pump available in the market and what are their cost. And like for example, like as you go for higher pressure drop pump, higher pressure developing pumps, then their cost is increasing, and it's increasing exponentially. So based on that, there is a limiting point that after which you go, then the cost of pumping increases. The increase in is very steep, very high increase. So so somewhere there we can put our limit that okay, up to this pressure it is okay, but if you're going beyond that pressure, then the cost is increasing more. So there we can decide, okay, this is our pressure constraint. So based on that, in the book, they decided that the 70 kilopascal is the pressure limiting criteria. So in both of these, like for the pipe side and annulus side, our pressure is well within the limit. So there is no issue for the pressure drop, right? So the velocities are within the constraint, the pressures are within the constraints, the material is as per the constraint, copper, and so this design is now complete. So this is your new heat exchanger performance. We have not taken into account the falling film falling coefficient we have not taken. So this will be the performance for the new heat exchanger.
Yeah, Doctor, if it is out of constraints, like the pressure drop is high,
Good.
like so we change the analyst diameter.
Yeah, very
to
good.
get larger one.
Okay. First of all, which pressure is out of the limit, for example? Pipe side or annulus side?
Analyst side.
Annulus side. If it goes the annulus side, then the one of the option is that you choose larger annulus, 1 or 2 step more, bigger size, right? So when your size is increased, then your velocity will reduce and the pressure drop will reduce.
Okay.
And if it is on the pipe side, then you have to change the both. You have to change the pipe also. And when you change the pipe, then accordingly you have to change the annulus also. Okay. And then what about the length? If the length come out to be very large, then what would you do?
We divide it to like in series.
Yeah, the one option is that you arrange the many heat exchangers in series. This is one option. Or the second option is that if the length is coming out to be very large, that means your double pipe heat exchanger may not work. You have to go for some other kind of heat exchanger, maybe shell and tube heat exchanger. Okay. Okay, so this problem is complete now. So similar type of problems. Another, it was the design problem where the heat exchanger was not given. And for analysis type of problem, the heat exchanger dimensions are given. So you have to move on after the heat exchanger dimensions to find out the temperature and outlet temperatures and so on. Another quantity they calculated here is the effectiveness. What is the effectiveness? So for the effectiveness, what is the formula we used if we want to calculate effectiveness of the heat exchanger? What is the formula? Can you tell me the page number? Which formula we are going to apply? Page number or slide?
Table 4.5. I don't know. From the slides, slide 28.
From the slide. Effectiveness. Effectiveness formula are not in the table. At the end, you mean the very last?
No, slide 28.
Okay,
From the slide.
I'm checking it. Right, correct. On that slide, yeah. Effectiveness. So effectiveness.
Second number.
Yeah, effectiveness for double pipe, one for parallel and one for counterflow. Okay, so you need to calculate C and N. What is C?
C.
C is the capacity ratio.
The minimum.
Yeah, that is basically the calorie ratio, that is C MCP over MCP, MCP minimum over MCP maximum. So you can see which one is minimum. So cold fluid is minimum, which is 5,000, and warm fluid is more, which is 13,000, right?
Yes.
So you can calculate what is the effectiveness. So MCP dt, MCP dt. Oh, sorry, this is only MCP. We're not talking about MCP dt. Okay, so it come out to be 0.4. It come out to be 0.4. 5,400 divided by 13,000. It's come out to be 0.4. Okay, and what is N? We have not been mentioned here N. What is N?
Number of transfer units.
How would you calculate number of transfer unit?
Overall, heat transfer coefficient multiplied by the area divided by the minimum capacity.
Okay, find out N. How much is this? Calculate N.
Yeah, 1 second.
So you want number of transference, doctor?
Yes.
Okay. But which area do we use? We use A0?
Yes.
Okay.
(1.7 to the power of minus 4).
Sorry, again.
1.7 to the power of
1.7
minus 4.
e minus 4.
Yes.
Okay. 1.7 e
4,
minus 4.
not 7. You write 7.
Okay.
Zero 0.1741.
Is this?
Yes. This is what.
Okay. And we know that if we know the effectiveness and if we know the NTU and C, we can find the final temperatures. But final temperatures we have already calculated, so no need to find. If you want to check, you can check that final temperature is again come out to be the same. But we have calculated the final temperature. So the before we calculated the final temperature, that was from the heat balance. But here you are calculating the final temperature. This is from the heat exchanger parameters, because the number of transfer unit is a heat exchanger parameter. C is a heat exchanger parameter, right?
But doctor, how you got number that small? I got 0.174.
Ask Sultan. He
Sultan, what did you do?
got this number.
I calculate the. Yeah, we have U2000. Okay, again to confirm it. Maybe I made a mistake.
Because this is very small. Usually it doesn't come this small.
Yeah, 0.17.
Alhamdulillah.
0.17.
17.
0.17. Okay.
741.
0.17.
41.
41. Okay, good. Okay, so we calculated all these things, right? Okay, so I think now you got the calculation idea that how we are going to do the calculation for these things, right? Okay, so before we finish, any question if you have?
No.
Any one of you recording this meeting or not?
I am not.
Nobody, yeah, because I forgot to record it and then it's not recording. And then it came to, and it's just, I remembered when it was very late.
Doctor?
Yeah.
For the, what you call it, boiler selection.
Okay.
So we just like choose it based upon the space we have in the house.
Based upon the space, that is your constraint, and based upon the requirement.
For example, I don't mind if I wait 5 hours to wait for the heating.
Sorry,
Is it fine?
it's depending upon the user. Eh? If you don't mind, if you need to wait for 5 hours. Okay,
Yes.
fine. As long
So
as
there's not much like calculations behind this.
no, there's not much calculation. Not much, because
Okay.
MCPDT will give you the idea what is the capacity. In that capacity, you decide, okay, how many hours you are running, and then that's it. Kilowatt hours.
Okay. So we don't even need to use the flow rate of the
MCPDT,
hot water.
flow rate we will need. MCPDT.
But how do we use flow rate if the boiler is a tank and there's nothing flowing inside because it's a storage tank?
It will increase the temperature. because MCPDT, you know, the MCPDT will give you the watt, right? What is the unit for MCPDT?
No,
CP?
MCP that you give joule because M is mass, right? Of the
Mass flow
water
rate.
inside.
No, flow rate. M dot basically flow rate.
But
MCPDT.
flow rate, what?
Flow rate
It's
of
a big tank.
no. You calculated the flow rate. You calculated all the flow rate, right? And
Yes.
and you calculated that you need to increase the temperature of this flow rate from this temperature to this temperature. So basically you have the temperature difference and you have the flow rate also, because this flow rate, you need to increase the temperature from this temperature to that temperature. Is it right?
Yeah, but doctor, he
Yeah.
means that when the water enters the heater, it will store. It will be stored
No,
there.
I will come.
As a,
I will come to that point. First of all, like that you have a certain flow rate, which is m dot, and you
Yes.
have
Yes.
to increase the temperature. So you're multiplying by Cp, and then you are increasing the temperature, let's say from T1 to T2. So when you calculate this thing, then this thing come out to be in watts. The unit will be watt, right?
yes.
Okay.
Yes.
Now, if and this watt is to be converted into the boiler specification wattage, that what watt boiler do you need. So the Q equals to, but in the boiler there is no flow rate, only the tank size, only the capacity, maybe like 5 liter, 10 liter or 20 liter boiler, right? So let's say it is
Yes.
20-liter boiler, for example. So you only have mass, you do not have mass flow rate. So the mass
Yes.
multiplied by Cp and multiplied by dt, that what temperature rise you need, right? Clear?
Yes. Yes.
Okay. Okay. For the safety reasons, the boiler temperature, you will temperature rise. You can decide, let's say it can go up to the 50-degree rise, not more than that, or 40-degree rise, not more
Yes.
than that. So I can choose, let's say delta T, I am choosing that at any instant, the boiler can raise up to 40-degree. So it is going to be, let's say 40-degree, and Cp I know for water, and capacity of the boiler, let's say it is 25 liter. So I can change it into mass. So now my unit is energy, right?
Yes.
Now my unit is energy. Okay.
Yes.
So this much energy you are giving to the boiler in what time? In what time?
Okay.
Then divided by the time. As you
You
said
mean
that
what?
you want to run it for 5 hours or something. So if you're dividing it by 5 hours, then it will be what? Right?
Yes.
Yes.
Then it will be what? So that will be the wattage of the boiler.
So that's where we got like that. We use the mass flow rate to get the watt at the beginning.
Sorry, tell it again.
At the beginning, doctor, you said that we use the mass flow rate.
Yeah, in the beginning I
So
said that the mass flow rate multiplied by Cp and multiplied by the temperature difference, and then you get, let's say you get 5 kilowatt,
yes.
and that 5 kilowatt you are equating it, making it equal, right?
Yes.
This is you are making it equal to
Yes.
m, the size of the boiler multiplied by Cp
Yes.
and multiplied by dt. So anything
Yes.
unknown can be found from here, like what should be the, and divide by the time also, sorry, divide by the time also, 5 hours or whatever. So anything
But
unknown, yes.
but the source of hot water is separate than the source of the cold water. They don't mix with each other, I think.
Yeah, they don't mix. So you need to find what is the need of the hot water. You have to find the need of the hot water. How much hot water you need.
But I think
So
they don't use like hot water and cold water. They use heating elements in the heaters.
Yeah, they use the heating element in that. Yeah. So if you're using the running water, let's say if you are using the running water, So for the running water, for your flow rate, because your flow rate is, let's say, what was the flow rate? Just give me the rough estimate. What is your flow rate?
90 centimeter cube per second.
Okay, 90 centimeter cube per second is your flow rate. Let's say you are having the line heater. Line heater means that immediately your water is heat up. Okay.
Yes.
Okay. So this much is the flow rate, and multiplied by Cp and multiplied by the temperature difference. So the temperature difference, that you want to increase the temperature by 10 degree or what?
By say 30 degree.
30 you cannot, because in winter you are getting like 10 or 15 degrees Celsius already, and then you want to increase it. So you can increase like up to 25, 26 or what? Or 30
Yeah,
degree,
okay.
15 degrees Celsius. So let's say 15 degrees Celsius. So 15 degrees Celsius. So you have all these values, right? So all these values, and its unit is watt basically. So how much is this coming? Can you calculate? 90 centimeter per cube. So 90 into 10 raised to the power minus 6 is meter cube per second now. And then you multiplied by density. So it's kg per second now, multiplied by 4181, and then multiplied by 50. How much is this coming? Calculate.
15 degrees Celsius.
Yeah, 15 degrees Celsius.
It comes out to be something like 5.64 kilowatt.
5
Yes,
point, yes, it's kilowatts. That means that you need a boiler for this condition of 5 kilowatt. And this is I'm telling for running boiler, right? That will work as
Yes.
inline. Like you switch off the flow, your boiler is shut off.
Okay. But does it have like tubes of cold water passing through inside or something?
No, another type of boiler is that it heats up the water and store it. It heats up slowly, slowly, slowly. Then you don't need a very high power, high kilowatt boiler, because it will warm up the water gradually, and then you can use it over the time. Like for example, like in the daytime, you use the bathroom or washroom for around half an hour to finish off your
Yes.
things. But you can switch on the heater 2 hours before, and then it is heating up in 2 hours. So the 2 hours heating, you want to utilize just 10.5 hours, right?
Yeah.
So for that,
Yes.
you don't need a very high capacity boiler. You just need a low capacity boiler. It will keep heat up, and then. So if you want to do like that, like instead of, because we just calculated this is the capacity for the line heater, but if you don't want to use line heater, then you can increase the time. For example, you want the same capacity, but your time is doubled. When your time is doubled, then you can divide it by 2. You can use the half capacity, your time is doubled.
Okay.
So that
But,
the warm water will be stored in the tank, and you can use it.
okay. What do you mean by a line heater, doctor?
Line heater is like that we have water line heater is that when you open the tap, at the same time the heater will be on. At the same time the heater will be on, and you will have the water at the set temperature. And when you close the tap, the heater is switch off.
Okay. So it's not something like heat, because there also I saw there are tankless water heaters.
Yeah, this is a tankless type of water heater, line heater, because there is no tank.
So
it is just flowing. There is a plate,
So
or
it's
there is a heater. Water will flow over it, and it will be warmed.
okay. So it's like it's the cold water that is being heated.
Yeah, cold water that is being heated.
So we can
Okay.
choose tankless or with tank.
You can choose anyone.
Okay.
If you choose tankless, then your calculation should be based on tankless. If you use
Just like calculate m.cb delta t and equate it to the power required.
Yes.
For the heat. Okay.
Yes,
So we
it's-
need to
it's-
consider
it's-
the efficiency.
it's very simple calculation basically. Yeah.
So for the tank water heater is more simpler than tankless water heater, right?
No. Tankless water heater
Another
calculation is simple because this is what I just showed you. The 5 kilowatt, that is the tankless line heater.
Okay. But that means that if you choose, you can only choose to have cold water or hot water. You cannot have both at the same time, right?
In this case, you cannot have both at the same time. Yeah. No. You can because what you will do, you will connect the line heater with one line, and other line is free of the heater. So you can have both hot water and cold water at the same time.
And you can have both at the same flow rate as well.
Why not? You need
Oh.
to select the you need to select the boiler as per your flow rate. Then it will provide you that flow rate.
Okay, I see.
You got it?
I hope so.
Yeah, like when the pipe is coming from the tank, you divided it into two parts. In the one part you connected with the heater, one part you did not. Okay, so the one part you will receive the cold water, other part you will receive the warm water because it's passing through the heater.
Yes.
And if you want to mix them, then you can put a mixer, like the kind of mixer we have in our kitchens. You just turn left or right, and then you can have a mixing of the two waters.
And we can maintain.
Nowadays we have it right in our washrooms and kitchens. You got it?
Yes.
Yes.
Yeah.
It's just a matter of like branching the pipes and these things.
I cannot hear you, Hadi. What do you say?
So it's just a matter of branching out the pipes and these things.
Sorry?
It is just a matter of branching out the pipes, right?
Yeah. You can branch out. Yes. And this is how the piping network we have in our university houses. And when I was living outside, it was like same. The main one pipe is coming from the tank, and then it is branched into two. One is going to the heater, another one is going to another one is normal direct supply. And when and they are meeting, they both come to the same basin, like it is kitchen sink or it is wash basin. Both are coming at that, and there either you can mix them or you can use them separately.
Oh, okay, I see. All right. So there is some sort of heating coil there.
Yeah, heating coil, heating plate, some sort of.
Oh, okay, I see. Okay, I hope I got it.
Okay, inshallah. Anyone else?
Inshallah,
There are
thank
several other members in the showing that others members also joined. Any question from them? Anything? Salim, Imad, anyone? Al Khatab, any question? Or they just joined and left? That is also possible, eh?
Maybe.
No, doctor, I am here also.
Salim is here, okay. Imad also, eh?
Yeah.
Okay, any question? Because
No,
I think
all good.
you joined from the beginning or you joined later?
No, at around 4:30.
Okay, so from which calculation you joined?
When we were calculating the analysts, N analysts.
N.
I think.
N.
Yeah, the one.
N was very late, not N.
Uh,
You can see, I'm sharing this screen. You can see my Excel file.
Yeah, the second row of the.
Okay,
right
N.
next,
No,
yeah,
Nusselt number.
Yeah.
Nusselt number.
Yeah, Nusselt number for the analyst.
Okay, what about you, Salim?
I came from the beginning.
From the beginning.
When you repeat the steps from.
Okay.
Four,
Okay.
I think.
Okay, then you understand. Okay,
Yes.
okay, I'm just repeating quickly, so then you can try by yourself, right? So this is a problem that in this problem, it's a design problem. The heat exchanger was not given. So we have to select the heat exchanger for our application. They mentioned that there is a kerosene and there is water, and kerosene is to be heated from 24 degrees Celsius to 35 degrees Celsius with the help of water. So we need to select a proper heat exchanger. The properties of the kerosene was given. Even if it is not given, we can take from the property table. So that is not important. For the water, we need to take the properties. Only one temperature was given, 95. So we can take the properties at appropriate temperature. We can see that what is the temperature difference here, basically 10 degrees Celsius. So approximately we can assume that there will be 10 degrees Celsius temperature here. This is just for idea, right? If our idea is wrong, then we have to repeat our calculation. So if we assume here the 10 degrees Celsius temperature difference, then the average will be 90 degrees Celsius, and then you can take the properties at 90 degrees Celsius. You got my point?
Yes.
Okay, so now the property things are done. And then we have to see that the two fluids, how we are going to route them. Kerosene, where to use, and water, where to use. Because one is a pipe and one is a annulus section. So in the last, so in the chapter of double pipe heat exchanger, when I was doing that, I explained the criteria for the routing of the fluid. So based on that criteria, we can choose that which fluid we should route to the pipe and which fluid we should route to the annulus. And this is the table you can see on the screen. So we took the criteria of the viscosity, that the viscosity for the kerosene is higher, so we took it into the pipe. So the kerosene we are taking into the pipe, and what we know about the kerosene is the mass flow rate is given, all properties are given, temperature is given, and the economic velocities are given. So based on the economic velocities and the mass flow rate, we can see that what is the minimum area required and what is the maximum area required. And then we can go to the standard tables, and we can see that which standard fitting in this limit. So we found that 1.5 standard is fitting in this limit, because 1.5 standard, the area was 0.00118, which is within these two numbers. Okay, so now we selected that the 1.5 standard will be for the pipe. And then for the annulus, we do not have all information to exactly calculate that what annulus size we should choose, because we don't have the mass flow rate that is flowing in the annulus. So what we did, we choose 2 step higher, 2.5, 2 step higher standard. And then we calculated the area of the annulus. So the area of the annulus we calculated, and the formula, all formula are given basically in the book, so you can check the formula in the book. So now we have the area of the pipe also and area of the annulus also, because we have selected both pipes, annulus also and pipe also. So we can calculate the velocity for the pipe. For the annulus, we cannot calculate velocity because we do not have mass flow rate. So for the annulus, we will select the economic velocity from our side. But as for the pipe, we need to calculate because we have the mass flow rate. So we calculated the velocity for the pipe, and then we choose the velocity for the annulus. So now we have the velocities and we have all the size. And then we calculated the hydraulic diameter for the annulus. Formula is given, direct substitution, find out the hydraulic diameter. Equivalent
Doctor,
diameter.
the velocity of the annulus is from the economic range of water, right?
Exactly. There is economic range 1.4 to 2.8. So you can choose anywhere between 1.8, 2 or 2.2, 2.1, whatever.
Okay.
Okay. And then we calculated hydraulic diameter, equivalent diameter. This is direct substitution. And now we can calculate the mass flow rate in annulus, because now we have chosen the velocity and we have the cross section area and we have the density, right? So we can calculate the mass flow rate. So we calculated the mass flow rate for the annulus. And then we calculated the Reynolds number for the pipe side. Then we calculated the Reynolds number for the annulus side. And then we calculated the Nusselt number for the pipe side, Nusselt number for the annulus side. So Reynolds number formula is same, rho BD. The only difference that you need to understand that when you are calculating the Reynolds number for the heat transfer calculation, then use DE for annulus. And when you are calculating
Okay.
the Reynolds number for pressure drop, then use DH for annulus. For the pipe, it is always diameter, inner diameter.
Okay.
Then you need to calculate the Nusselt number for pipe and Nusselt number for annulus. The formula is given in the book. It was, what was the page number? Anyone can remind me? It was on the page number 417. 417 is, it's for laminar flow, and 418 it's for turbulent flow. So depend upon the Reynolds number, we calculated the Nusselt number, and then we calculated the HI and HP. On the same page it is given. And then we calculated the overall heat transfer coefficient. Okay. So we need to calculate the MCP. So MCP for the cold fluid is our kerosene. MCP for the warm fluid is our water. So we calculated them, and then we calculated the rate of heat transfer. So the rate of heat transfer, we have three ways of calculating it. Either you can calculate it for cold fluid, or you can calculate it for warm fluid, or you can calculate with the help of heat exchanger parameters. So our kerosene is warm fluid. So the kerosene, we have the mass flow rate, we have the CP, and we have the delta T. So we can calculate the Q here. So we calculated the Q here. And the same QC, we equated it with QW. QC equals to QW. And what is QW? The mass flow rate of warm fluid, which is mass flow rate of water. CP of warm fluid, which is CP of water. And delta T, that is T1 minus T2 for warm fluid. So the T1 is given 95, T2 we can find by equating the heat transfer. So once you find the T2, then all the four temperatures we have. Then we calculated the log mean temperature difference. Log mean temperature difference for, so here you can calculate it for laminar flow or for counterflow. So we, parallel or counterflow. So we calculated for counterflow. And the formula is given in your book, so you can use that formula for log mean temperature difference. It was equation 8.10, I think. 8.10, yes, 8.10 on page number 407. Okay, and then we need to calculate the area subjected to heat transfer, A naught. So the A naught is equals to pi ODP multiplied by L. Pi DL, basically. Pi DL. So the D means ODP, pi DL. And then we calculated this. Okay. So, but a length we don't have. So we need to calculate the length, right?
Yes.
So for calculating the length, first we calculated the overall heat transfer. First we calculated the area subjected to heat transfer using the heat exchanger equation. What is the heat exchanger equation? That is Q equals to U A LMTD.
Yes.
U multiplied by A multiplied by LMTD. So we have U, we have LMTD, we have Q. So from here we find the A.
Okay.
So when we find the A, after that we find L, because A equals to pi DL. Okay. Clear? Is it clear?
Yes, it's clear. We use the D for the annulus.
We use ODP for pipe, outer surface of the pipe.
For pipe, outer pipe. Okay.
Yeah, outer surface of the pipe. And so here we find the L also. And then we need to calculate the pressure drop.
Effectiveness.
Yeah, here we are calculating the effectiveness. So effectiveness not required in this question, but I calculated it. So we can check the formula. What is the formula for effectiveness? And we can use it directly. C also, it is direct formula. And T2 is again direct formula. So these three steps like this, 1, 2, 3, it is not related to this problem basically. But, these 1, 2, 3, 4 is not related to this problem. These are the extra parameters. I just showed that if you want to calculate, how to calculate. So these are direct substitution in the values. But what we need to calculate in this question is the pressure drop for the pipe side and pressure drop for the annulus side. For the pipe side, pressure drop calculation is exactly same. There is nothing changed what you have in your chapter 5 and 6.
Okay.
So you use the formula, and the formula is given on page number 421. The formula are given. So what we need to calculate is the friction factor for pipe side and friction factor for annulus side. So the friction factor calculation, again, you know, it is depends upon the Reynolds number, and it depends upon the epsilon over D.
Epsilon.
Epsilon over D. So when you are calculating for the pipe side, then it is epsilon over IDP. And when you are calculating for the annulus side, then it is epsilon over DH.
DH. Okay.
Okay, so then you calculate the friction factor for pipe and friction factor for annulus, and then substitute in the formula on page 421 to find out the pressure drop. So, and then we check that the pressure drop, how much is it? It's coming out like 3.6 kilopascal, 6.19 kilopascal. So we need to check in our solution that the pressure drop should not go very high, length should not go very high. So it should be within the constraint. So for the pressure drop, like the constraint is 70 kilopascal, and length should not be very high. If it is very high, then you have to suggest like what kind of design is it? Is it a series connected, or what kind of design is it?
Okay, doctor, understood.
Yeah. So this is it about this problem. Okay, any other question?
No questions my side, doctor.
Okay, then we close this session, and tomorrow also we will see at 4 if there is any further question, because not many people joined today. Probably the same thing, I have to repeat it tomorrow, or additionally something more like if we finish this quickly, then we'll do something else also tomorrow, inshallah.
Inshallah.
Okay, so we can conclude this here.
Okay, thank you, doctor.
Okay, thank you for joining. All the best. And you have seen the quiz schedule already, right? So the next quiz will be on
Yes.
this chapter, double pipe heat exchanger. That is on 14th or when?
14th.
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 Okay, inshallah. Okay then. Okay, thank you.
See you. Take
Assalamu
care.
alaikum.
Thanks.